This is the second video for section 2.6 where we'll talk about the derivative of the inverse sine function, sometimes denoted sine inverse. This is also called arcsine. So if you see arcsine or sine inverse, those are the same functions. So remember the graph of the sine function. It's this nice periodic oscillatory function that goes through 0 at 0 and looks like this. Now, we want some way to define the inverse of it. So we want to define a function that undoes the sine function. Unfortunately, sine is not a one-to-one function, meaning it does not pass the horizontal line test. So it doesn't have a well-defined inverse. But since it is periodic, we get all of the information about the sine function in a restricted interval. So I can restrict the sine function for the purpose of defining the inverse to this little blue section of the sine curve. So notice here, any horizontal line I draw intersects the blue piece at most one line. So this is a one-to-one function restricted to the blue piece. So for the purposes of defining sine inverse, we're going to restrict sine to the closed interval from minus pi over 2 to pi over 2. And if I restrict sine there, I'll define arcsine, or sine inverse, to be the inverse of the sine function. So we'll define arcsine to be the inverse of sine x, but we have to restrict the domain of x. So x has to be less than or equal to pi over 2 and greater than or equal to negative pi over 2. So by definition, what does that mean? That means arcsine of y equals x is the same as saying sine x equals y. So arcsine and sine undo each other. And the domain of our restricted sine x is the closed interval from negative pi over 2 to pi over 2. The range of sine x, our restricted sine, and in fact our unrestricted sine even, is from negative 1 to 1, the closed interval. So the domain of arcsine is going to be the same as the range of sine, so its domain is going to be from negative 1 to 1, including the endpoints. And its range is going to be the domain of our restricted sine function, which is from negative pi over 2 to pi over 2, including those endpoints. And the graph, we can get the graph of arcsine by reflecting that blue section of the sine graph over the line y equals x. Now, I find it a little bit confusing to look at both of those pictures on the same graph, but you should confirm that indeed this picture that I've drawn is the reflection of that restricted piece of the sine graph about the line y equals x. So notice this has x values between negative 1 and 1 and y values between negative pi over 2 and pi over 2. So this curve looks like a nicely differentiable function on its domain. It doesn't have any vertical tangent lines or any points or anything, cusps or corners. So let's take the derivative of it. And you've seen already the derivative of natural log. And like I said, deriving formulas for inverse functions are going to follow the same pattern. So we're going to start with our cancellation equation, and we're going to put arcsine on the inside. So sine of arcsine of x equals x, as long as x is in the domain of arcsine. Now telling you about the domain is not strictly required for this proof, but I just want us to get in the habit of making sure we're paying attention to where these functions are defined. So now I take the derivative of both sides. So for the time being, I'm just going to write the derivative of the left side as d dx of sine of arcsine of x, and then the derivative of the right-hand side is just 1. So now I'll use my chain rule on the left-hand side, and I'll have cosine of arcsine of x times the derivative of arcsine of x, which is what I'm trying to find, so I'm going to leave that alone for now, equals 1. And then I can solve for the derivative of arcsine of x. It's just 1 over cosine of arcsine of x. Great! But that's kind of ugly. Cosine of arcsine of x. it turns out we can get a slightly nicer formula that, in fact, perhaps surprisingly until you see the argument, does not involve trig functions at all. So let's see how we can simplify cosine of arcsine of x. So let's let theta, I'm just going to give the arcsine of x, I'm just going to call that a different variable. So I'm going to call it theta. Because really, if you think about how you defined your trig functions, the sine function eats an angle, theta, and returns a number. So that means since arcsine is its inverse, it's going to eat a number and return an angle. So theta equals arcsine of x is equivalent to the equation sine theta equals x. So what I'm going to do is I am going to draw the triangle, the right triangle, that has angle theta, and I am going to label its opposite side x and its hypotenuse 1. So notice that this triangle, if you remember your SOHCAHTOA, sine of this angle theta is equal to x over 1, or is equal to x. Okay? So now I can use the Pythagorean theorem to label my third side of this triangle. Namely, it's the square root of the hypotenuse squared minus my other side squared. So the square root of 1 squared minus x squared, which simplifies to the square root of 1 minus x squared. Okay, so I've labeled three sides of the triangle. Now what am I interested in? I am interested in cosine of arcsine of x, which is cosine of theta. So on this triangle, cosine of theta is adjacent over hypotenuse, so it is the square root of x minus, it is the square root of 1 minus x squared over 1, which is the square root of 1 minus x squared. So my conclusion, which you already saw, was that cosine of theta, which is cosine of arcsine of x, is just the square root of 1 minus x squared. So then my final conclusion, if I go back to my formula for the derivative of arcsine of x, it is 1 over cosine of arcsine of x, which is just 1 over the square root of 1 minus x squared. So notice that I get a formula for the derivative of arcsine that has no trig functions in it. Also notice that this is only defined on the open interval from -1 to 1. Because if I put in -1 or 1 here, I get a 0 in the denominator. So my derivative is not defined. So here is an example of a function where the domain of the derivative is smaller than the domain of the original function.